Imagine a flag, really taut, snapping hard in a strong wind. Almost looks alive, doesn't it? Now think about that same kind of force hitting an aircraft wing. What happens then?
Yeah, that's not a pleasant thought.
Exactly. It brings us to our topic, flutter. It's this potentially catastrophic vibration in aircraft design. It's been a problem since, well, basically the beginning of flight.
And the old ways of fixing it always meant adding weight, which is never good.
Right. But maybe that's changing. Today we're diving into the X-56A unmanned research aircraft. People call it the MUTT.
Catchy name.
It is. And it's on this really groundbreaking mission to tame flutter using active control, something really new.
Active control, yeah. That's the key difference.
So we've looked at some specialized sources for this deep dive. A profile from a carbon fiber drone maker, a detailed aerospace magazine piece, and an overview from the defense contractor.
Good stuff.
The goal is really to unpack the engineering, the design choices, the collaboration behind it all, give you a solid picture of how they're trying to shake things up.
Okay, so let's talk flutter itself, because it's not just a little wobble, right?
No, definitely not.
It's a violent harmonic vibration. Basically, it happens when the aerodynamic forces the air pushing on the plane interact with the way the structure itself naturally wants to bend and vibrate. It's structural dynamics.
No.
When those two things couple, kind of like microphone feedback,
Right.
it can build up uncontrollably. And, it can literally tear a wing or a tail right off the aircraft.
Oh, so it's like that flag analogy again. The wind hits it, and it doesn't just wave smoothly.
No, it pulses.
It dips and swells, almost really that induced pulsation. And if it's too much, rip.
Exactly. That's flutter in a nutshell, just with much, much higher stakes on an airplane.
And this has been a known danger for how long?
Pretty much since powered flight began, over a century. And even now, predicting exactly when it will happen is still surprisingly difficult.
So designers have always had to sort of build around it.
Yeah, mainly by adding stiffness. You just make the wing structure really rigid, beef it up, hoping that prevents that destructive coupling.
But that adds weight.
A lot of weight, which
Okay.
means more fuel burn, less range. It's always been this big trade-off, a major limitation.
That's why Ed Burnett, the X-56A technical program manager, called it a particularly nasty dragon that lives in one corner of the sky.
That's a great description, because it really is this monster lurking there that you have to design around.
Okay, so that's the problem, the traditional fix, the dragon.
Yeah.
But the X-56A comes at it completely differently with this active control. What's the core idea there?
Well, instead of just brute forcing it with stiffness, the idea is to use the aircraft's own flight control systems, the same ones that provide stability, to actively counteract the flutter vibrations as they start.
So the plane fights itself, in a way.
Kind of. Or maybe learns to dance with the forces. It senses the vibrations starting and uses its control surfaces like ailerons in tiny, rapid movements to damp it out before it grows.
Wow.
It's teaching the aircraft to actively suppress these aeroelastic instabilities in real time.
And that sounds revolutionary. Not just fighting the symptom, but changing the dynamic.
Exactly. It's a fundamental shift.
And the payoff, if it works, huge, right? You could use longer, more flexible wings.
Lighter wings.
Much lighter. And that means aircraft that can fly higher, potentially faster, definitely farther on the same amount of fuel, or carry more payload. It opens up the design space enormously.
So you can see why the X-56A looks the way it does, that blended body, the long, thin, swept wings, thin airfoils.
Yeah.
It's a glimpse of the future.
Absolutely. It's designed with those future long-range aircraft, manned or unmanned, and fuel-efficient transports in mind. It embodies that potential.
And this whole effort, aiming to predict and actively suppress flutter, was funded by the U.S. Air Force Research Lab, AFRL. Yes, they clearly saw the strategic importance of breaking free from those old constraints.
Okay, before we get deeper into the tech, let's talk about that name. MAD, M-U-T-T. It's memorable. Where did it come from?
It's actually two acronyms combined. MAD is for the test program, Multi-Utility Aeroelastic Demonstrator.
Okay.
And MUTT is for the aircraft itself, Multi-Utility Technology Test Bed.
Ah, MAD, M-U-T. Clever.
Yeah, and they leaned into the dog theme. There were two identical aircraft built. The main one was named Fido.
Fido?
Yeah, apparently from their team slogan, "Flutter it, drive on."
Ah.
And the backup was named Buckeye after the AFRL program manager's dog and also his alma mater mascot. They even painted little dog tags on the underside.
That's brilliant. Adds a bit of personality. So what are we looking at size-wise?
It's 480 pounds, Got a 28-foot wingspan, about 7 feet long, and stands maybe 5 feet tall at the wingtip.
So decent size, not a little model.
No, definitely a substantial research vehicle. It took about 18 months to build the 2 airframes.
And a really key part is the modular wing system. 2 different sets of wings.
That's right. Critical for the testing. First, you have the stiff wings. Built the traditional way, beefed up structure, thick carbon fiber skins. Designed not to flutter in the test envelope.
For baseline checks, airworthiness.
Exactly. Then you have the flexible wings. These were the interesting ones. Deliberately designed to flutter within the flight envelope.
Wow.
Yeah. And the key thing is, both wing sets share the same internal structure, the carbon fiber spars and ribs, but the flexible ones have these very thin fiberglass and foam skins.
So the only major difference is the skin, controlling the flexibility.
Precisely. Allows them to isolate the effect of the active controls.
And swapping them isn't too bad.
Relatively speaking, yeah. External mounts make it easier. It takes about 15 hours, they said, which is pretty quick for this kind of work.
And there's a clever safety feature with those flexible wings too, right? Something about fuel.
Yeah, this is neat. They have internal water tanks and pumps. The water simulates fuel weight.
Ah, so if a wing does break during flutter testing.
You spill water, not jet fuel. Much safer for pushing boundaries.
Makes sense. And they build spares.
3 identical sets of the flex wings, just in case. When you're designing something to potentially break.
Good planning. And it wasn't just one type of flutter they were after.
No, they were targeting 3 different modes, aiming to suppress them all simultaneously. There's body freedom flutter, or BFF.
Okay.
Then symmetric wing bending torsion, where both wings bend and twist together.
Like flapping symmetrically.
Right, and anti-symmetric wing bending torsion, where they bend and twist opposite each other.
More complex, so tackling a whole symphony of flutter.
That's the goal, a really ambitious one.
What about power? What makes it go?
2 small jet engines, jet cat turbines, about 80 pounds of thrust each. One source mentions P240s installed by MTC Corp. Another article cites P400s. Might have been an upgrade or variation.
And their placement is important too.
Very. They're mounted close together on the fuselage, importantly, out of the main airflow affecting the wings.
Why is that?
To avoid propeller wash, essentially. Or, in this case, jet exhaust turbulence. They didn't want the engines themselves inducing vibrations or noise that could contaminate the sensitive flutter measurements. Keep the data clean.
Makes sense. Okay, so we have the structure, the wings, the engines. How does it actually see and gather data during flight? What's the instrumentation?
It's got a pretty good sensor suite. Up front in the nose, there's a forward-looking camera for the pilot on the ground. Standard for UAVs.
Right, remote piloting.
And right next to that camera, interestingly, a small microphone.
A microphone, why?
For situational awareness. It lets the pilot actually hear the aircraft, the engines, the airflow, gives them another sense of what's happening.
That's clever, like hearing your car engine.
Kinda, yeah. Also on the nose are the GPS and communication antennas, and they apparently have some cool flying tigers-style shark mouth art painted on there.
Nice touch. What about monitoring the wings themselves during flutter?
They have cameras on the fuselage pointed out at the wingtips, specifically to record flutter events visually. And on the inside surface of the wingtips, there's a grid pattern painted.
A grid?
Yeah, it provides a visual reference. So when the wing starts fluttering, they can see it against the grid and actually measure the amplitude, how much it's bending and twisting. Quantifiable data.
Very practical.
And, some of the other details really paint a picture of this kind of research project. It feels real, but scaled.
Like what?
Well, they use little wooding wheel chocks. The remove before flight streamers are actually just keychain fobs. And during pre-flight, they use a shop vac, basically, blowing air into the avionics bay to keep things cool.
Resourceful. It shows that blend of high-tech goals and practical, maybe even slightly improvised solutions you sometimes see in R&D.
Exactly. Solving complex problems with whatever works, combining advanced tech with hands-on ingenuity.
This sounds incredibly complex to actually build. Who put the MUTT together? You mentioned MTC Corp.
Yeah, MTC Corp played a massive role. Lockheed Martin actually brought them in to build the 2 carbon fiber airframes for NASA.
So Lockheed designed it, MTC Corp built it.
Largely, yes. MTC Corp handled a lot. They designed and made all the CNC tooling needed. They manufactured the 2 fuselages to spec. They produced the 4 wing sets, both the stiff carbon fiber ones and the flexible fiberglass ones working from Lockheed's designs and CAD data.
Wow, that's extensive. The whole structure, basically.
Pretty much.
Yep.
Then they did the final assembly, the painting, and critically, they installed the jet engines, the sensors, actuators, controllers, all the wiring, the instrumentation.
System integration, too.
Exactly. And then they did the power-up checks, the initial system tests, making sure everything worked according to the aerospace specs. They really delivered the ready-to-test vehicles.
That's a huge responsibility. And they continued working on the program. You mentioned the X-56B.
Right. They also machined the flexible wing sets for the X-56B variant, working with Northrop Grumman and AFRL. The X-56B kept the center body but used a blended wing body design.
A different aerodynamic shape.
Yeah, testing similar concepts on a different platform configuration.
And MTC Corp has the credentials. AS9100, ISO 9001.
Yep, all the key aerospace certifications. ITAR registered, Gulfstream approved supplier even. Their codes cover composites, machining, aerospace manufacturing. They have the chops.
But here's the really amazing part I found. This X-56A was apparently the first flyable aircraft that MTC Corp, or GMFI Aerospace and Defense, as they were also known, had ever built. They were better known for building custom cars.
Get out! Really? Custom cars?
That's what the source said. How does the company go from custom cars to building a cutting-edge experimental UAV for NASA and Lockheed?
That is remarkable. It suggests, well, first, a high degree of skill in precision manufacturing and composites, which you definitely need for high-end custom cars.
Yep.
And maybe complex system integration, too. But adapting to aerospace tolerances, documentation, safety standards, that's a huge leap. It speaks volumes about their capability and maybe the transferability of those cool skills.
It really does. Shows innovation can come from unexpected places.
Definitely. Cross-industry expertise paying.
So this ambitious project didn't just appear overnight. What were its origins?
It actually goes back quite a way to around 2005. It started with smaller independent research contracts focused on what they called the Body Freedom Flutter Program, or BFF.
BFF?
Yeah. And the approach was kind of wild. They built 5 small vehicles, like 10 pounds, 10-foot wingspan, carbon fiber, and styrofoam, hand-launched.
Tiny.
And they were essentially designed to break.
Designed to break.
The whole point was to push them into Flutter, to gather data, and crucially, to demonstrate that they could predict it accurately and even actively suppress it, even on these small, fragile test beds. Prove the concept.
So fail fast, learn fast, but on a small scale first.
Something like that. It laid the groundwork.
And it strikes me that none of this, the X-56, the active suppression, would likely have been possible without the huge leaps in computing power.
Absolutely not.
Ah.
The miniaturization of computers in the late 90s and then the massive increase in processing power since the early 2000s, that was the enabler.
You needed that power for the real-time calculations.
Exactly. Running those complex active control algorithms, sensing the flutter, calculating the correction, actuating the control surfaces, all in fractions of a second. That just wasn't feasible before computing caught up.
Technology enabling the breakthrough. So before the first flight, they did static tests. You mentioned something almost old-fashioned.
Yeah, they used lead shot bags, piled them on the wings on the ground to simulate the loads the wings would experience in flight. A technique right out of the 1930s, really.
Wow, a bit of old school meets new school.
Shows that fundamental engineering principles still apply even when you're doing cutting-edge work.
And then the first flight, June 26, 2013, at NASA Dryden, Edwards AFB, in a historic hangar.
That's right, the same hangar where they prepped America's very first jet, the Bell XP-59 back in 1942. Pretty cool connection to history.
Definitely adds some resonance. And Lockheed test pilot Mike Hartenstein was at the controls, remotely, obviously.
Yep, and apparently the test card for the flight had a little drawing of a dog wearing goggles on it.
Love it, keeping the theme alive. So the flight test had phases. Stiff wing first.
Correct. Phase 1 used the stiff wings. They did about 8 flights, roughly 25 minutes each, through September 2013. Mostly envelope expansion, checking basic handling, airworthiness, pushing the speed and altitude gently.
Building confidence. Then phase 2.
Phase 2 brought in the flexible wings. This was a core of the research, developing the flight control laws, the algorithms, basically tuning the system so it could actively suppress the flutter modes while still flying the plane stably.
That sounds incredibly complex, making it feel stable even when the wings are designed to wobble.
Yeah, making it appear rigid to the pilot's inputs, even though the structure is flexing. Those control laws were finalized in fall 2014, a major achievement.
And the work continues. Skunk Works and NASA working with Buckeye now.
Right, they're using Buckeye, the backup aircraft, for NASA's own flight test program phase, building more competence in the control system, particularly with the stiff wing configuration, likely informing future aircraft programs.
It really underscores that this X-56A isn't just the airplane itself, it's a whole system.
Totally. It's a complete research ecosystem. You've got the ground control station, for instance.
Developed by Skunk Works.
Yeah, and they built it cost-effectively using commercial, off-the-shelf gear inside a commercial trailer.
Smart. What's the setup inside?
You've got the pilot and the test director side by side up front, test coordinator behind them. Then along the sidewall, consoles for the flutter engineers and the flight control engineers monitoring all the data, and a test data conductor in the back managing the data flow.
A mobile command center.
Pretty much. And it's not just the control station, they have simulation capabilities too.
To practice.
Exactly. Rehearse the flight tests in the simulator before doing it for real. Reduces risk, plus a system integration lab to test components together on the ground.
And they even have dedicated trailers for moving the aircraft.
Yep. One main transport trailer for the X-56 itself, and another small flatbed trailer used for towing it on the ground and for doing ground communication checks. The whole logistics package is thought out.
So bringing it back to the listener, why should you care about this? About the MAD, MUTT, and flutter suppression?
Well, because this research has direct implications for the future of flying.
How so?
If you can reliably suppress flutter actively, you unlock those lighter, more efficient wing designs we talked about. That means potentially more fuel-efficient airliners, longer-range cargo planes, maybe even a higher-performance military aircraft. It could affect cost, range, environmental impact.
So it fundamentally changes the design trade-offs.
Exactly. It helps us understand these aeroelastic instabilities much better, letting designers push boundaries they couldn't before, moving beyond just building around the flutter problem.
It really feels like the X-56A, the MAD, MUTT, marks a potential turning point, tackling this century-old challenge with active control, innovation, collaboration. It's quite a story.
It absolutely is. It shows how persistent problems can be overcome with new thinking and new technology. It's not always about brute strength. Sometimes it's about intelligent control.
Building smarter, not just stronger.
Precisely.
So here's a final thought to leave you with. If actively suppressing flutter really does allow for these radically different wings, super long, thin, flexible, what could that mean for how airplanes look in the future? Could we see designs that blur the lines even more between what we think of as a fixed-wing aircraft and something more organic or flexible?
That's a fascinating question. Could aircraft aesthetics change dramatically? It certainly opens up possibilities beyond the shapes we're used to seeing. Something to ponder.